A good day to all. This is Dr. B. Amini, Assistant Professor, Department of Networking and Communications, School of Computing, SRM Institute of Science and Technology, Katangaluttur. In this video session, we are going to see about design of lexical analysis using Lex tool under Unit 1 of Compiler Design subject. So, to start up with, the lexical analyzer generator using Lex tool. So we all know that there are 6 basic phases are there in a compiler. The first one is lexical analyzer phase, second one is syntax analyzer, third one is semantic analyzer, and the fourth one is intermediate code generator, fifth one is code optimizer, and the sixth one is code generator phase. The first phase is the lexical analyzer phase, which takes the source program as input and produces the stream of tokens. So this lexical analyzer phase will get a command from the syntax analyzer phase stating that get a token command from the syntax analyzer. On receiving it, this lexical analyzer phase will generate the stream of tokens. Okay, so here for generating this lexical analyzer phase itself, we are going to use a tool called as Lex. So Lex is a tool for generating lexical analysis phase to recognize the tokens using regular expression. So this program generates lexical analyzer. It is used with Yak parser generator. Yak is nothing but what? Yet another compiler. Why it is used with Yak parser? In sense, the parser, that is the syntax analyzer phase, has to give the get next token command to the lexical analyzer phase, which produces stream of tokens. That is why. So yet another compiler parser generator is also used here in this part. The lexical analyzer, where and all you seeing in your code, you are seeing it as YY, which means that there is a parser involvement in that. Okay, the lexical analyzer is a program that transforms an input stream into sequence of tokens. Okay, fine. So in this entire video, that is the entire video session is divided into two. One is learning of Lex program and its structure. The other one is the design of lexical analysis phase. So the first one is Lex language learning, so which has 4 parts. The first one is use of Lex, second one is structure of Lex program, and the third one is conflict resolution in Lex, and the fourth one is look ahead operator. So first one, use of Lex. So what is the use of Lex? This Lex tool is going to generate what? The lexical analyzer phase. How it is going to generate the lexical analyzer phase? So the Lex compiler initially gets the source program lex.l. This program structure and its features and all we will be studying in the next slides, forthcoming slides we will be studying. Okay. So for the Lex compiler, they will be giving a .l extension file, which is a Lex file, will be given as input so that it produces a .c file. And already told you, wherever you see Y, there will be an involvement of what? There is an Yak parser, that is parser is also involved in it. Okay, so it generates a C file lex.yy.c. okay, fine. So this lex.yy.c is given as input to the C compiler. Since it is .c extension, it is a C program which is given as input to the C compiler, which in turn produces what? A.out. This A.out is nothing but what? Your lexical analyzer phase. To this lexical analyzer phase, if the source program is given as input, then it produces the sequence of tokens or stream of tokens has been given as output. Okay, so this is what called as use of Lex. And coming to the structure of the Lex program, the Lex program structure is being divided into 3 parts. The first one is declaration part, and followed by what? Translation rules, and the third one is auxiliary functions. Okay, declarations, what are all the variables you are having, what are all the declarations you want to declare, everything you will be having it in declaration part above the translation rules. So the translation rules are separated from the declaration and auxiliary functions using 2 mod symbols. So that is what been mentioned here, 2 mod symbols. What is the pattern? That is, what is the rule of writing a translation rules means? It will be starting with a pattern and followed by what action has to be taken for that particular pattern. So will be defined like this. And auxiliary functions are the functions that is purely specific for the program, will be defined in auxiliary functions. So this is for declaring declaration part, and declarations of all the variables or the instances, whatever you are having in your program, that will be in declaration part, and the translation rules of form, pattern and action. And the next one is auxiliary functions, which will have the functions only, right? So structure of a Lex program. What is the structure of a Lex program? In a global variable YYL, that is, this is a YYLVal is a global variable which is going to hold some values only, which is shared between your lexical analyzer phase and the parser generator. Why? Because after generating the tokens, the token has to be placed in the symbol table, which will return the token has to be placed in the symbol table, and which will return a token ID that will be stored in YYLVal, which will be which will be used by the syntax analyzers also. Okay, so the YYLVal is it is to return both the names called, that is already told you in specification of tokens, like a token is a pair of token name and attribute values, right? For that, one ID will be written and that will be kept in YYLVal. And there is another set of auxiliary functions you will be using. One is install ID and the other one is install num. So install ID is to install ID function is to use like this, that is in input buffering there are two pointers. One is lexeme beginning and the forward pointer. So the lexeme beginning will point to the first lexeme beginning points to the first letter of the lexeme, and the forward pointer will move on. Once it finds some blank space, if this lexeme matches the pattern, then announces this is a token, right? So this is what happens. So the install ID is called to place the lexeme found in the symbol table. So the install ID is called, this install ID function will be called to place the lexeme. Whatever lexeme you find, that lexeme, that is to place the lexeme found in the symbol table. You see that this install function will install the lexeme into the symbol table. Okay. And YYLVal, this we have seen already. The function returns a pointer. On installing that lexeme into the symbol table, the function will return a pointer which is placed in what? YYLVal. Okay. So note that install ID has available to it two variables. They are set automatically by the lexical analyzer that Lex generates. Okay. Another two variables are there. One is, other than your YYLVal, there are two other variables. One is YYText and the other one is YYLength. YYText, in input buffer, the lexeme points to one location, one character, that character will be held in YYText. And YYLength is nothing but the lexeme length will be identified by the found lexeme length will be identified by the YYLength. Okay. And the token name ID is returned to the parser. Yeah, after placing this particular lexeme into the symbol table which matches the pattern, it identifies it as a token. Place it in the symbol table along with the pair. Pair means token name and the attribute for which an ID will be assigned. That ID will be returned to the parser. Okay. So the action taken when a lexeme matching the pattern number is similar, using the auxiliary function install num. So now only on install num, it will give you a number that will be returned to the parser. Okay. So here is the program structure. See here, there are three parts are there. One is the declaration part. This is the declaration part. Between two mod functions, the transition rules will be defined, and this is the what do you say? This is the auxiliary functions. Okay. So see here. Okay. So now this is the regular definitions. Okay. So the first one they have defined. So before going to the regular definitions, we will go for definitions. So LT is less than equal to, not equal to, greater than or equal to, if, then, else, ID, number, relational operators. These are the definitions. These definitions has to be given some values that will be given in your translation rules. Okay. So what is this then? These are the definitions. That is what the declarations we are going to have. Delimiter. Delimiter is of three types. One is a white space can also be called as a delimiter, and \t is also called as a delimiter, tab space, and \n, which is nothing but a new line feed, will also be called as a delimiter. And WS is white space. White space means what? A single white space or a many number of white spaces together will be called as a delimiter, right? White spaces. So that is why they have mentioned plus over here. Letter. How will you identify a letter? Capital A to the alphabet, set of alphabets of this letter is nothing but capital A to capital Z, small a to small z. Digit are from 0 to 9. ID is nothing but what? Letter. It must start with a letter followed by letter or a digit, that to 0 or more times. And a number already we have defined in your specification of tokens. So digit a single digit may be there, number of digits may be there, at least one digit must be there. That is why this plus is being given. So dot, it may start with a dot followed by any number of digits or even a single digit, and question mark they have given. Question mark they have given means 0 or 1 instances. If it appears, it will appear for one instance, or else it will not appear at all. So this e function will appear for one instance or it will not appear. So e followed by plus or minus, that too, this digit may appear 1 times or 0 times, that's it, right? So plus, digit plus may appear. So the entire session may apply, this entire thing may appear within this open parenthesis and close parenthesis may appear for 0 or more instances. Okay, so this is the declaration part. Now coming to the translation rules. What is a translation rule? So white space, if this pattern is taken, no action will be taken. So if this is the pattern, no action will be taken. That is for white space, you are not going to do anything. So no return will happen. And if the pattern is if, then the return will be capital IF. It is a keyword. If the pattern is then the action for that it is starts to return capital THEN. If the pattern is else, then the action corresponding for that is return ELSE, capital ELSE. And if this is the identifier, if any identifier is found, then the identifier has to kept in the symbol table. How it will keep it in symbol table? Along with the token name, its attribute will be kept in a symbol table, for which an install number will be activated, and it returns a number that will be placed in YYL1, isn't it or not? So that is what. So for identifiers, install ID will be enabled, and that install ID will return an ID. That ID will be assigned to YYL values. Okay. Similarly, if you found a number like constant, it has to install number, any number here. If it is an identifier, you will install identifier. If it is a number, you will go on install with number, right? You will initiate an install num function, and it returns a number, and that number will be an integer type which will be assigned to YYL1. Okay. Now what about less than, equal to, not equal to, greater than, equal to? So the less than symbol, if it find, then the relational operator will return, that is the relational operator will be returned, that will be stored, that value will be stored, that integer value, what number is being for that relational operator, that will be stored to YYL. Okay, so similar to that, less than, equal to, not equal to, greater than, equal to will be obtained. And install ID, already I told you, in symbol table it is going to place the token, like same if you found, that will be placed in the token name, and the attributes will be placed, and it returns an integer value, the ID will be returned. Okay. And install num, similar to install ID, here the number is going to be put into the symbol table. So similar to install ID, puts the numerical constant into the separate table. So this is all about the structure of the Lex program. See here, this is the declaration part, translation rules, and the auxiliary functions. Okay. So now coming to the third point of your learning, Lex, conflict resolution in Lex. Say for example, if I am getting it as less than symbol, clearly I will state that it is less than symbol. If I am getting it as equal to symbol, then clearly I will state it as what? Equal to symbol. If I am getting a statement that is symbol like less than, equal to, together, at this point what should be defined na? The Lex program itself should be in a right way of understanding things, like you have to write a program like that for Lex in order to take the longest prefix than that of the shortest prefix. See, if less than, equal to is there, instead of less than separately, equal to separately, it is going to take, it has to take together as what? The longest prefix. So the longer prefix has to be considered rather than less than separately, equal to separately. So that is, always prefer a longer prefix to a shorter prefix. So if the longest possible prefix matches, so okay, you found less than or equal to, you have found as the longest prefix. So now this matches 2 or more patterns. Yeah, this matches 2 or more patterns. Less than pattern also it is matching, equal to pattern also it is matching. Prefer the pattern listed first in the Lex program. So what is the pattern that has been preferred first in the Lex program? Less than is there, and if you get next to that equal to, not separately you can have, but less than symbol, after less than symbol you are having less than equal to, right? So this is before equal to symbol you are getting it as like less than equal to. So which means that if the longest possible prefix matches two or more patterns like less than or equal to, prefer the pattern list first in the Lex program. The first pattern is less than, but it is not defined immediately with equal to the equal in the next step, but the next step is less than equal to, which is the first pattern. So we have to consider this as the longest prefix of less than equal to. Clear? And now the look ahead operator. What is a look ahead operator? See, for example, int space a is a statement in my program. Declaration part I am having. So the lexeme begin will point to I, and the forward pointer will move from I to n, n to t, and from t to white space it will go, isn't it or not? So on reaching the white space only, it will confirm that I and t is a keyword. You can ask me why, ma'am, why can't the forward pointer on reaching the t itself, it can declare it as like a keyword. Say for example, int 1 is not a keyword, it is an identifier. So in this case, when it identifies I, n, t, that time itself if it declares it as a keyword, then it is a wrong. So which means that on reading the white space only, it will come to the conclusion that int is a keyword. No more extra characters are added to that keyword. It is exactly matching with the pattern what has been described for me. Like that the program will assume. This is what the operations of look ahead operator. Also see here. So in Fortran and some other languages, keywords are not reserved. Okay. So for such case, say for example, this is an array and it is not a keyword. IF is an array name, and within bracket I comma j is two-dimensional index, two-dimensional array. So this statement contrasts with statements of the form. This is similar to the form what? If condition then statement, isn't it or not? So this is similar. So on reading this, this should not, they should correctly identify that if is a keyword or it is a array, right? So for which the logic can be written like this. The look ahead operator can be written. If IFF, it must have a space followed by dot, star, and a backslash symbol and a letter. So this backslash symbol is used between your open parenthesis and the closed, that is left parenthesis and the right parenthesis. Okay. So see here. So this rule says that the pattern lexeme matches is just the two letters if, right? So the lexeme matches is just two letters if. So the slash says that says that it is an additional pattern followed by does not match with the lexeme. So it does not match with what? Lexeme. So since it is having a gap, right? The slash it is there. So it does not match the lexeme. And in this pattern, the first character is left parenthesis. Yes, of course, it is a left parenthesis. Since that character is lex meta symbol, this symbol is called as what? Lex meta symbol. So it must be preceded with a backslash. This is an important symbol in this statement. So this is a lex meta symbol which must be preceded with what? Preceded with a backslash. Yeah, of course I have put it. And there is a thing followed, that is dot and star. So dot and star match any string without new line. So in between this, that is after open parenthesis, you can have any string without a new line. Okay. And that dot is a lex meta symbol. Again, dot is a lex meta symbol, meaning any character except a new line. So any character except new line. So this together na any string without a new line, and this is a meta symbol which is any character except a new line. So which will be followed by a right parenthesis. Since this is a lex meta symbol, it must be preceded with what? A backslash. So and then it is followed by a letter. So this is how the look ahead operator has to be defined for finalizing the lexeme. Okay. So far we have seen about what? The learning of lex thing, that is lex tool, lex programs. So the first one is first one is use of lex, that is .l extension to .c extension to a dot dot is the lexical analyzer which takes input in one form, produces output in another form. The second one is lex structure of a lex program. So declaration part, translation rules and auxiliary functions. Translation part, how it will be, pattern and examples. An example for that has been given here, wherein we have seen about YY text, YYLVL, install ID, install number, and then what else we have seen? the declaration part, the translation rules, and the auxiliary functions. Okay, so the next one is conflict resolutions. Instead of shorter prefix, you have to prefix a longer prefix, and then less than equal to that conflict and all we have discussed. Okay, and then the look ahead operator. So for finalizing the keyword or the identifier, you have to use the specific format like backslashes to in front of preceding with lex meta symbols. Okay, so this is the keyword for that, and the learning phase of the lexical analyzer program is over. Okay, now we are going for a design of lexical analyzer phase. So the design of a lexical analyzer generator, under which we are going to see 4 topics. The first one is the structure of the generated analyzer, pattern matching based on NFAs, DFAs for lexical analyzers, implementing the look ahead operator. Very easy topic it is actually. Why? Because we are going to start up with regular expression, then regular expression to NFA conversion, from NFA to DFA. That indirect method we have seen, no, Thompson's construction method, from regular expression to NFA, NFA to DFA, and finally we are going to discuss about some look ahead operators. That's it. Okay, so the structure of the lexical analyzer. See the structure of the lexical analyzer. A lex program will be given to lex compiler, which in turn produces a C program. C program will be given as input to the C compiler. So that C compiler will produce a lexical analyzer, which means that a transition table and actions will be there, and which will be an automaton simulator from where it can read the input buffer with lexeme begin and forward pointer on match. This lexeme matching with the pattern will be found as a token and given to what? The symbol table. This is what the finite automata simulator. Now it's clear, right? So this is the structure of the generated analyzer. And the next one is under the structure of the generated analyzer itself, a transition table is meant for, so from regular expression you are converting into an NFA, right? NFA to DFA you are doing, right? So for which you will be having a transition table for the automaton, those functions that are passed directly through the lex to the output. The actions from the input program which appears as fragment of code to be involved at appropriate time by the automaton simulator. Okay. So now coming to the next one, second point, second heading is pattern matching based on NFAs. See, you all know what you'll be having number of patterns, and for which every pattern you'll be generating the NFA, and for which you'll be going for some actions A1, A2, A3, or the actions for the pattern. Okay, that is what you'll generating here as NFA diagrams. So an NFA constructed from a lex program is being given like this. Okay, so now let us consider A is the action 1 for pattern P1, ABB is the action 2 for pattern P2, A star B plus is the action 3 for pattern 3. Okay, now how to draw the NFA diagram for this? So how will you draw the NFA diagram? Simply for A, it is a simple statement. For this action 1A, it is a simple statement. From one state to second state, it will move on with an input symbol what? A. And the second one is ABB. For ABB, similar to that ABB I have drawn here. And the next one is A star B plus A star, which means A star means what? 0 or more times of A. Even if the A may not appear, that time it has to straight away take the B value, which must be present at least once. So A straight away takes the B value, which will be at least present once, and B plus, plus means what? 1 or more times. So this is the 3 NFAs for A, ABB, A star, B plus. Now on combining, because we are going to combine from a single state, on combining everything, we are going to have the structure like this, right? A separately, ABB separately, and then A star, B plus separately we are having. Now, I want to trace out the input like what? AA, BA I want to trace out. So now I am going to start from 0. So where and all I can go for A? Here also one A is there, here also one A is there, here also one A is there. So I have to reach all the 3 points. So that from 0, 1, 3, 7 I am going, right? 0, 1, 3, 7 I am going. Okay, fine. On taking the input A, the next input is nothing but what? Again another 1 A. So when I go with this direction from 0 to 1, only 1 A I can take. So this is going to be kept out. It is out of scope. And now I'll go for this. Now on going for this, now I'll go for this. Okay, 1 A is over. And for another A, it's going to be B then. So this also cannot be taken. Now from here, the second A can be taken since it is 0 or more times. 1 A is also taken. Second A is also taken. After AA, it's B. So only this region I am going to do, that is 0 to 2, 4, 7, right? So it's nothing but what? 2 I have reached, it is not working. 4 I have reached, it's not working. So I'm going for what? 7. Okay, 7. So on A input, only I am choosing with what? 7. Yeah, fine, I am chosen with 7. From 7 I have to go for B. Yes, I could go for B, 8. Okay. So B is been traced, and the final one is A. So here I am in, when I reach here, the next element that I could take is only B, not A. But I am expecting A, but I could reach only what? B. So this BA cannot be generated by this NFA diagram. Clear? So this input is the sequence of set of state enters when processing the input BA, which cannot be generated at all. So for this NFA diagram, we are going to have a DFA diagram. See here, this is the DFA diagram for the NFA diagram, whatever we have drawn for A, B, A star, B plus. Okay. So this is the A state, that is 0, 1, 3, 7 is the A state, B state, C state and D state. Okay, see. A state, B state, C state and D state. Okay. C state and D state. So this is while combining the DFA, you will be getting extra final states. Okay. On drawing this diagram, now we are going to trace out what? The same input BA. Okay. So from here, if I start, I have only A this side B. So I cannot go this side. So I have to come by this way. What is the input? The next BA. So the next A I have to take. So if I go by this way, I cannot go over, but here I can take it AA, right? That is what? BA. So when I'm going with like this, when I reach the 68, this value if I'm reaching now, 68 I'm reaching now, how I can reach A, B and B? I am getting only B, right? So I couldn't find it as like what the input, sorry for the taking that input. The input here is A. So when I take the input A, it has to take from A, then B, then B. And here it is a final state from where you cannot go with what? Another, right? So but I am expecting another A here, but with ABB itself it is getting stopped over here. From here I cannot move further. So this input has not been accepted by this DFA diagram. Okay, clear? Any doubt in this? So this is about DFAs for lexical analyzer phase. The final thing is implementing the look ahead operator. So as we seen that Fortran example I have given for look ahead operator, no, that has been given in the diagram, NFA diagram. Okay, first it analyzes I. If it matches the pattern, then it goes for analyzing F. That is, the forward pointer will move on and analyze the F. And if it finds the empty spaces, then that time it will come to know that if is a keyword. Then it proceeds with open parenthesis and any input string and close parenthesis, finally the letter. So this is how the implementing of look ahead operator has been done on finding the empty space that lies between 2 to 3. So this is what the implementing of look ahead operator. So in this second half, we have seen about the design of lexical analyzer generator with 4 different subtopics. One is structure of the generated analyzer, pattern matching NFA, DFA for lexical analyzers, implementing the look ahead operators. So the structure of the generated analyzer is this one, wherein Lex compiler is used for generating the translation tables and the actions, and with the help of simulators you will be proceeding with the scanning of input. That is, scanning of input is nothing but lexeme finding, and that will get updated in the symbol table. So this is what the components used for it, and the pattern matching based on NFAs is being defined with the diagram. For the example A, B, A star, B plus, and for the same NFA is being used for tracing the input string BA. And with the same example input, we are tracing another input like A. So at 68 it will get stopped because ABB can be generated, but then ABBA cannot be generated for the given regular expressions, okay, in the NFA. And finally implementing the look ahead operator has been implemented. So that's all about the today's topic of design of lexical analyzer and the lexical program learning and all. Okay, so thank you all. Thank you.